Dear students, today we will be discussing on solar air heater and its performance analysis. So, what is solar air heater? So, solar air heater is a thermal device in which the energy from the sun is captured by an absorbing medium and is used to heat air. This solar air heating is a renewable energy heating technology used to heat or condition air for buildings or processes application. So, other applications are drying of agricultural products, industrial process heat and space heating. Okay? So, as far as solar air heating is concerned, so what are different components of a solar air heaters? One glass cover at the top, then we need to have an absorber plate and then duct through which air flows. Okay? So, this may be the inlet of the air and this may be the outlet of the air, from where you can collect the hot air and use it for applications. And also we need to provide sufficient insulation to reduce the heat losses which is generated inside the air heater. Okay? So, these are the insulations in the bottom side. Of course, we need to apply some kind of insulation in the sides as well. Okay? So, this solar air heater eliminates the need of transfer of heat from one fluid to another fluid, because in case of liquid flat plate collector, what happens? So, heat will be absorbed in the absorber plate, then that has to be transferred to the fluid. Okay? So, that part is not required here. Okay? So, that is why it eliminates the need to transfer heat from one fluid to another, right. And as I have shown that it consists of an absorber plate with a parallel plate below forming a small passage through which air to be heated, right. So, this transparent cover is provided above this absorber plate for transmitting solar radiation to this absorber plate, and then finally we need a sheet metal container with insulation to hold the structure, right. This solar air heater face area ranges from 1 to 2 meter square, similar to what we have considered for liquid flat plate collector. The material of construction and size are similar to those used in liquid flat plate collectors. The absorber plate is a metal sheet of thickness 1 mm, usually made of GI or steel. GI means galvanized iron or other material, okay, derived from steel. And this thickness of this glass is about 4 to 5 mm. Okay? And nowadays plastics are also used in this kind of air heaters. Okay? Mineral wool or glass wool of thickness 5 to 8 centimeter is used for reducing the heat loss, okay, at the bottom and side, right. And finally, that the whole assembly is contained in a sheet metal box and inclined at a suitable angle, which is tilt angle to be maintained, okay, which was discussed in the last class. What angle will be appropriate for a certain locations. So, what are advantages of using this solar air heater if we compare with a liquid flat plate collector? So, in case of solar air heater, corrosion and leakage problem is very minimal, okay? And the solar air heater does not require any special attention at temperature below 0 degree Celsius, but in case of liquid flat plate collector, we need to think about it, right. If it goes below 0 degree and if we use in a place like Ladakh, then what will happen? It will freeze if we use water in that flat plate collector, right. So, we need to use different kind of fluid so that it will not freeze if that ambient temperature goes below 0 degree C, right. So, this is one special advantage of this solar air heater. And what are the disadvantages? Like heat transfer coefficient between the observer plate and the air is low, which results in lower efficiency. Okay. And in this case, large volume of fluid have to be handled. Hence, this electrical power required is very high if the pressure drop is not kept within the prescribed limits. Okay. So, these two are very, very important aspect we need to look into as far as design of a solar air heater is concerned. And of course, we can increase the heat transfer coefficient by different means. Two of the means are doing roughened surface, so that no turbulence can be created. If we can increase the turbulence, then we can augment the heat transfer coefficient. And sometimes longitudinal fins are also used, okay, to increase the heat transfer from the plate to the fluid, right. So, there are different types of solar air heaters. What you can see, there are three configurations. So, in the first configuration, what happens? We have this glass cover, one indicate glass over and two indicates observer plate and three indicates this bottom plate. So, here in the first configuration, what happens? Fluid flows between this observer plate and this bottom plate, and this is a glass cover. Okay. And in the second case, what happens? We have glass cover and there is no bottom plate, only observer plate we have. And in this case, air flows between glass cover and observer plate, again between observer plate and this bottom plate. Okay. So, different types we can classify. Okay. And for all these types, we can have this kind of configurations. So, without fins, so sometimes no, we can use the solar air heater without using a single fin, and sometimes we can use multiple fins, okay, in order to augment the heat transfer coefficient, and also sometimes we can use this kind of configurations to increase the turbulence. And in all the cases, our attempt is to increase the heat transfer coefficient between the plate and the fluid. Okay. So, that is what it is shown in this slide. So, this slide shows the energy flow of a solar air heater. Okay. So, here if we use double cover here, okay, solar radiation falls here through this glass cover and it is received on the observer plate. Okay. So, energy is received here and then it is transferred to the fluid. Okay. Right. So, as you can see, if we consider this 100% energy is coming from the solar, okay, and then some of the energy is absorbed here in the observer, okay, itself, and since fluid is flowing from here to here, inlet to outlet, then heat will carry. So, it is found out that useful energy by the transporting medium carries 60% heat, okay, and then 10% goes to convective losses or convection losses, and radiation losses will be 8%, and re-radiation, once it strikes on this observer plate, it will re-radiate. Okay. This re-radiation loss will be about 8%. Okay. Of course, we need to estimate the amount of losses taking place from the bottom of the collector, which is estimated to be about 4%, right. So, all these things we can know write in terms of thermal resistance. Okay. So, if we consider this QU, which is useful heat gain. So, this the amount of heat which is goes out, okay, for utility, that is nothing but useful heat gain. Okay. And what happens when solar radiation is falling on this device? So, the radiation transmits through this glass cover, it is received on the receiver, again heat exchange will be there in between this observer and this back cover. Okay. So, when heat exchange will be there, then what happens? Some amount of heat will be absorbed in this plate and then this also contribute in increasing the temperature of this incoming fluid. Okay? So, if we consider this Tb is the temperature or say mean temperature of this bake plate, and Tp is the mean temperature of this plate Tp, okay, and in between fluid is flowing. So, this is the useful heat gain. So, fluid temperature is maybe Tf, right, at particular section or particular point. So, there will be heat exchange between this plate to this fluid, and then this plate, absorber plate to this fluid. So, this is from bake plate to the fluid, and this is from the absorber plate to the fluid. Okay? So, this is the one kind of thermal resistance. Okay? And top loss will be there. Okay? So, top loss will be there, and this estimates the amount of losses taking place from the top of the collector, right. And if we combine these two, what we will get? This is the heat transfer, okay. That is the amount of heat transfer what is taking place here in between these two plates. And then finally, we can estimate the amount of thermal resistance, okay. That is overall thermal resistance, or what we can say total loss coefficient, right. So, this way we can calculate, and also it tells the kind of heat transfer takes place in this solar air heater, right. Now, let us study the performance of a solar air heater. Okay. So, we will follow the analysis proposed by Wheeler. Okay. So, we need to draw the collector first, and this is a glass cover, and then we will have this absorber plate, and we will have again this is the bake cover, and of course, we will have this insulation. So, this is insulation, and we will have TFI will be here, TFO fluid outlet temperature is TFO, okay, and this is the heat transfer coefficient HFP, and this is heat transfer coefficient HFB from the bake plate, and we will consider a section here. So, this may be del x, and it will start from here, okay, and this may be TPM. So, mean temperature of the absorber plate, and this may be, we can consider TBM. So, this is the mean temperature of the bake plate, okay, and if we consider TF here, fluid temperature here, if this section delta x, if it travels, then maybe it will have some kind of higher temperature. So, TF plus dTF, right, and maybe I can consider eta P is the emissivity of this plate, and this eta B may be the emissivity of this plate, okay, and bottom loss will be there U B, and top loss I can represent by UT. Okay. So, this part, this length is L1 and width, so that way it will go, okay, so width will be L2. So, this is width and L2 one is the length from inlet to the outlet. Okay. So, now we will consider a slice. This is the slice, okay, and width is L2. So, along this direction, and the thickness is delta x at the distance x from the inlet. Okay. So, that is shown in the figure, right. So, before we derive the expression for QU, so we need to assume some of the parameters like temperature changes from TF to TF plus dTF in the section dx, m is the air mass flow rate, okay, which is constant, and Tpm is the absorber plate temperature, and Tbm is the bottom plate temperature, and this variation of Tpm and Tbm are neglected, okay, and side losses are neglected, okay, and also we will learn at what condition we can cancel UB, okay. Now, energy balance for the observer plate we can write. So, this is the amount of radiation which is falling on the section what we have considered. So, this S into this part is L, L2 by del x. So, this will go something like this. If we visualize, this will go something like this, okay. So, delta x, so this will be something like this, okay. So, this delta x multiplied by L2, this is the area multiplied by S, the amount of solar radiation received at that section. So, equal to some losses, stop losses, and then heat exchange between this plate to the fluid, okay, and then heat exchange between this plate. This is absorber plate, already you know, ABS absorber plate, and then this is bottom plate, okay. So, this radiative exchange will be there in between these two plates, right. So, that way we can develop this energy balance for the absorber plate, okay. So, this is the losses, and this part is a heat transfer from plate to the fluid, and this last portion is for the radiative exchange between both the plates. And then we are interested about energy balance for the bottom plate. Now, we are interested about this bottom plate, okay. So, what will happen? So, this bottom plate also contribute to this fluid, because already some amount of energy is absorbed here due to this exchange. So, heat will be giving to this fluid, and then radiative exchange will be there in between these two plates, okay. So, that way we can develop. So, this is the radiative exchange between these two plates, and this is the heat exchange from this bottom plate to the fluid, and then this is the bottom losses, okay. So, from here we will have bottom losses. So, losses will be there, and then heat exchange between the plates and the fluids. Then we are interested about energy balance for air stream. So, air entry is there, okay, air entry is here, and then heat transfer or energy is coming from both the plates, okay. So, that way, so mCp dt, the amount of heat finally is gained, is equal to Hf L2 dx, this is the area in that segment, and Tpm minus Tf, that is the plate to the fluid, and then this is for absorber plate to the fluid, and this is the bottom plate to the fluid, okay. So, again there is an assumption that we can assume this Hfp is equal to Hfb, okay. This is the heat transfer coefficient between the fluid and the plate, and then fluid and the bottom plate, right. So, now we will introduce an equivalent radiative heat transfer coefficient HR, which is defined something like this, okay. So, HR Tpm minus Tbm is equal to sigma divided by 1 eta p, which is the emissivity of the absorber plate. This eta b is the emissivity of the bottom plate, minus 1 multiplied by this temperature, okay. So, Tp m to the power 4 minus Tbm to the power of 4, okay. So, this term is known as equivalent radiative heat transfer coefficient HR. So, for small temperature difference between the absorber and the bottom plate, okay, this temperature difference can be approximated as 4 T average cube. This T average is nothing but Tpm plus Tbm divided by 2, right. So, we can have this kind of expression, okay. So, already defined what is T average. So, if we use this, then this expression for becomes something like this. So, HR will be 4 sigma TAB cube divided by 1 by eta p plus 1 by eta b minus 1, okay. So, this is nothing but equivalent radiative heat transfer coefficient. Okay. Now, assuming UB is very less compared to UT. Okay. So, this UT is very high, okay, because to reduce the heat loss sufficient insulation is provided from the bottom. Okay. So, because of that this UB can be neglected compared to UT, right. So, under that condition this original equations are reduces to S is equal to this expression, and then HR will be something like this, and then finally this last expression. Now, when we talk about energy balance in the fluid, then this will simplify something like this. Then if we use equation 7 again to calculate TBM, so our expression will be something like this, and so this TBM is equation 9. Okay. So, this if we use this TBM and use the equation 6, then TPM will be something like this. Okay. So, where H is the effective heat transfer coefficient between the absorber plate and air, okay, which is given by something like this. Okay. So, this effective heat transfer coefficient is a function of heat transfer coefficient between plate to the fluid, then radiative part, and then bottom plate to the fluid, and then this expression, right. Then we can introduce this HC in equation 10, and we can have this expression. Okay. So, we will have m dot Cp dt to L to dx is something like this. This is an energy equation for the fluid, okay, or energy balance in the fluid, and then this substituting 12 in 13 what we have got in the equation 12, then we can simplify this equation and it will be something like this. Now, we can define this efficiency factor F dash or collector efficiency factor F dash, which is nothing but this. Okay. And this equation 14 becomes the following differential equation. Okay. So, we will get this kind of differential equation, and this can be solved by applying the boundary conditions Tf is equal to Tfi at x is equal to 0. Okay. So, if we solve this, then we will get an expression of something like this. Okay. Now, similarly, useful heat gain rate from collector can be calculated by using this expression, okay, where Fr is the collector heat removal factor. Okay. So, this expression is something like this, which is similar to the liquid flat plate collector what we have derived in the last class. So, if the assumption UB is very less compared to UT was not considered, then equation 16 would have been something like this, okay, where UL double dash is the equivalent overall loss coefficient and F dash and UL are given by these two equations. Okay. And UL dash will be something like this and HC will be something like this. Okay. So, we know now how to calculate Fr, how to calculate F dash, then we know how to calculate QU or useful heat gain of a solar air heater. Okay. So, now this QU can be related with TFI and TFO. Okay. So, this Fr is something like this. Okay. So, as you understand, in order to calculate those heat transfer coefficient like HFP, like HFB, okay, we need to rely on some kind of correlations. Okay. So, people have done extensive research and there are some well formulated correlations which can straightway can be used for calculation of these heat transfer coefficients. Okay. Some of the most widely used correlations as far as this solar air heater is concerned, the correlations developed by Case, which is something like this, and Malik and Bulow is something like this. Okay. And for this, as you can see, this Nusselt number is a function of Reynolds number in both the cases. Okay. So, when we are interested to find out this Reynolds number, we must know how to calculate the equivalent diameter. Okay. So, this equivalent diameter is defined as 4 into cross sectional area of duct into weighted perimeter. Okay. So, for example, if we consider a circular duct, okay, so what will happen? So, what will be the DE here? 4 into cross sectional area of the duct, it is pi d square by 4, and then we will have weighted parameter, which is nothing but pi into d, right. So, this 4 goes cancel, this finally d. So, for a circular pipe, so this equivalent diameter will be the diameter of the pipe, right. But in case of the section what we are considering now, okay, this kind of section, okay. So, if we know this B and then this is L, okay, we must know this area. Okay, DE will be 4 into cross sectional area is some, maybe this was L1, B into, so this is B along the length, maybe anything we can consider. So, here maybe I can say A, okay, otherwise it will be confusing. So, A into B, then we will have 2 into A plus B. Okay. So, that way you can calculate the equivalent diameter, okay, and that diameter is required to calculate Reynolds number. So, this RE is rho V d by mu. Okay. So, this diameter is considered sometimes, and this diameter is nothing but equivalent diameter now. So, it will be D or L, right. So, once you know this, then we can calculate Reynolds number by knowing these values at mean values of this plate. Okay. So, this P M and T B M. Okay. We need to take the mean of these two, means T mean is equal to T P M minus T B M. For any two parallel surfaces, if we know the temperature of these two surfaces, then we can find out what is the T mean. At this T mean, we need to find out the property of the air, and diameter is known. Then once you know this, then we can calculate what is Reynolds number or Reynolds number. Okay. And once you know, then we can substitute there and we can calculate what will be the heat transfer coefficient, because Nusselt number is known to us, H, L or D equivalent by K. Okay. So, from that we can calculate what will be the heat transfer coefficient, right. Also, we need to calculate friction factor for this kind of arrangement, okay, because as you can understand here we need blower to blow air. Okay. So, if we have very rough surface over which air flows, what will happen? Pressure drop will be there. Okay. So, pressure drop is directly related to the amount of power consumption. Okay. So, for that we need to find out F, friction factor, then we need to find out pressure drop. Okay. So, this is very important, because in solar air heater blower is one component which consumes huge amount of power. Okay. Just an example, if we know a value of Reynolds number for a flow, then we can find out what will be the F. Okay. So, once we know this F, then we can substitute in this expression which gives pressure drop. Okay. So, this is nothing but 4 L rho V square by twice dE, right. So, this pressure drop once we know, then we can calculate the power requirement and all. Now, let us discuss some of the experimental observations of different air heaters. So, here two air heaters are compared. In the first air heaters, what happened? Air flows within the glass cover and then one more glass cover, and under the beneath of this glass cover one absorber plate is there, and again air moves below the absorber plate as well. Okay. So, this is a bottom plate. And the second configuration, what happens? These two are glass cover and then air flows between glass cover and the absorber plate and then absorber plate to the bottom plate. So, it goes something like this. This is called two pass air heaters. Okay. So, in the first configuration, this better heat up to an inlet air temperature difference of 20 degree has been observed. But in this case, what happens? Better heat up or better up to an inlet air temperature difference of 50 degree C. Okay. So, as per the experimental observations, it is found that this outer glass cover temperature lowered by 2 to 5 degree by using these configurations, and efficiency of this type of collector is measured to be about 10 to 15% higher than a conventional air heaters. Okay. So, these are the developments. So, again here what happens? Porous medium is applied. Since porous medium is nothing but some kind of steel wools to increase the absorption of solar radiation, so that efficiency can be maximized. Okay. We have glass cover and then absorber plate and then we have bottom plate. Okay. So, this solar radiation and width of the flow channel are varied, and efficiency was found to be 70%, which is 10 to 20% higher than that of the collector without porous medium. Okay. So, in this kind of configuration, the outlet temperature of 90 degree C at a solar radiation of 900 to 100 watt per meter square can be achieved at a flow rate of 0.0995 kg per second. Okay. So, this is one kind of experimental observations where porous medium is used to increase the efficiency of the collector. Okay. Now, we will discuss some of the other solar air heater designs, mostly matrix air heater, then plastic air heater and transpired air heater. Okay. In all the three cases, collectors with porous absorber plates are used, and it yields higher efficiencies than conventional design. Because of large flow areas, these designs have small pressure drops. So, these are very important aspects of a solar air heater. Okay. Now, let us discuss first about matrix air heater. Okay. So, as you can see, its configuration is totally different than the conventional solar air heater. So, what you can see here, it is a cover. Okay. This is not a glass cover, okay, but is transparent. This solar radiation directly falls on this matrix absorber and air goes across this matrix. Okay. So, what is matrix here? This matrix is made by stacking wire screen meshes or slit expanded metallic foils, and normally very low cost material like glass beads, crushed glass wools, etc. are used as matrix media in order to absorb more solar radiations. And here what happens, when air moves, it gets more time to interact with the metals, which is heated up by using this solar radiation. Okay. So, in this kind of configurations, it is found that top loss is reduced significantly, and matrix provide large heat transfer area to volume ratios, and most importantly higher heat transfer coefficient due to increased turbulence of air flowing through the matrix, which is important. If you can increase the contact time, and roughness, then of course we can augment the heat transfer coefficient. And of course, higher collection efficiency can be obtained by using this kind of configurations. So, as per their findings or researchers' findings, with an air inlet temperature of 21 degrees C, the efficiency is reported to be about 75%, which is found to be quite good efficiency. So, there are some cases where this matrix can be used in 2-pass air heater. Okay. So, this is some kind of matrix, okay, in order to increase the outlet temperature of the heated air. Okay. So, this is glass cover, 2 glass covers, and then we have matrix, right. So, much higher efficiency than conventional air heater can be obtained, and pressure drop is high compared to conventional air heater. This is one of the disadvantages of this configuration. Okay. So, that has to be maintained properly, otherwise power consumption will be very, very high, right. So, pressure drop has to be maintained. And there are certain air heaters called plastic air heaters. Okay. So, in those kind of configurations, the absorber plate like porous black textile or polyester is used as absorber plate, and for transparent sheet polyvinyl chloride is used. So, this is a transparent sheet, solar radiation falls here, and absorber is some kind of porous black textile of polyester which is absorbed. It is a black surface, this is absorber plate, and air flows here. Okay. So, this is an absorber, this is a plastic cover, okay, but this is highly transparent, and air flows in between these. Okay. And it is a flexible plastic sheet, okay, it is a very, very flexible, and as per research findings, its area varies from 10 meter square to 20 meter square, and this wide is 1 meter. Okay. This is 1 meter, area is about maximum of about 20 meter square can be fabricated, and base thickness is found to be 6 centimeter. So, if we maintain 6 centimeter, then is the best efficiency is achieved, and efficiency reported to be 67.9% at a volume flow rate of 770 meter cube per hour, and then solar insulation of 759 watt per meter square. This is capital, right. And one more plastic air heater which is used for greenhouse has been shown here. So, here what happens, there are two parts, this is one part, this is the second part. In the first half or first part, only polyethylene sheets are used, and the second part another layer of plastic wrapping film with air bubbles to reduce the convective losses are done here. Okay. Then this greenhouse dryer are attached. So, there are different trays, so you can keep many agricultural products or other products for drying. Okay. And normally its length is about 5 meter and diameter is about 0.365 meter. Okay. And of course, this is suitable for agricultural product drying. And one more solar air heater, what you can see, this is nothing but inflatable tunnel plastic solar air heater. So, this is a blower, air is supplied from this blower, and there are number of trays where raw materials can be kept and drying can be done, and this is the exit part. Okay. So, you can see length is about 50 meter people have made, and this width is about 5 meter. Okay. So, this absorber is a layer of pebbles and is painted black. Okay. So, pebbles are used and it is black because of no, that has to store more thermal energy. The cover is a UV stabilized polyethylene sheets of thickness 178 micron, okay, the thickness of that sheet. Based on their observations, they found that after an exposure of 6.5 hours, outlet temperature was reported to be 53 degrees C at an airflow rate of 4.36 kg per second and insolation of 850 watt per square meter. Okay. Now, let us discuss about unglazed transpired collector on a vertical wall. Okay. So, this is a vertical wall, what you can see here, and this is plenum over which or say through which air flows, and this is a perforated absorber plate. Okay. So, this ambient air will move in through these small perforations. Okay. So, one blower will be here, it will suck, and then air will flow and it will be distributed as per this kind of perforation devices, okay, or say ducting, right. So, this kind of concepts normally applied in coal countries for space heating applications. Of course, this can be applied for crop drying and other agricultural product drying, and this porosity of this absorber plate is about 0.5% is maintained in most of the cases. As per the investigation, that mass flow rate varies from 0.01 to 0.05 kg per second per square meter, okay, and this plenum depth ranges from 5 to 30 centimeter. So, this is maybe 5 centimeter to 30 centimeter. Okay. So, this portion is known as plenum, okay, this portion. Okay. So, this is the wall. Okay. So, air will move through this and it goes there, okay, in the header, and then it will be distributed through ducts, okay, in order to maintain the room temperature, right. Now, you can see how this ducting is done. So, once we have this, then this blower will suck, okay, and then there are some holes or ducting or distribution ducting. Then, so this may be this may be for one room, this may be for one room, okay, or maybe two holes are for one room. So, that way this can be arranged and room heating can be carried out, right. So, as we have said, it is a dark perforated absorber captures solar energy, and this fan draws air through collector, okay, and controls regulate temperature, dampers and auxiliary heatings, and air is distributed through the buildings, and wall heat loss recovered. So, normally what happens, this wall heat recovery can be done by using this methodology, right. So, now let us solve one problem related to these unglazed transpired collectors. Okay. So, the temperature rise delta T of air through a vertical south facing unglazed transpired collector is found to satisfy the following empirical relation, which is delta T is equal to 0.03 IT plus 3.0, right. For an airflow rate of 36 cubic meter per hour per meter square of UTC, this IT is nothing but the total solar radiation incident on UTC, and delta T is in 0 C is in Celsius. Assuming this relation to be valid, calculate the efficiency of a vertical south facing UTC for the following data. Okay. So, we need to find out the efficiency, okay, eta I. The location is given as 28 degree 35 minute north and 77 degree 12 minute east. Okay. And date is December 10, hour angle is given as 15, then air flow rate is given, then global solar radiation Ig is given. Okay. And diffuse radiation is given as Id. So, once we know these two, then we can calculate what is Ib. So, this Ib can be calculated by deducting Id from Ig. Okay. So, it will be 543 minus 144. Okay. So, this will be 399 watt per meter square. And reflectivity of the surface is given as 0.2. Okay. So, we know what is instantaneous efficiency, right. So, this can be calculated by using Qu by IT into A. This area is that area, right. So, this is, so this area, this wall area we need to find out. Okay. So, this is the, so this wall area. Okay. So, we also know what is Q is nothing but m Cp or m dot I can write is delta T divided by IT into A. Okay. So, normally in case of conventional collectors we place AP or AC, but here what happens, this side, this wall area we need to consider. Okay. This wall area, we need to calculate. So, this is given, right, m dot by A is given, m dot by A is given here is 36. Okay. Then we have Cp dt by IT. Okay. This may be equation 1, right. And also we can simplify this m dot A. So, this is 36 cubic meter per hour per meter square. So, it will be 36 multiplied by density of air. So, it will be cubic meter per hour per meter square into kg per cubic meter. Okay. So, this will goes off, and then finally what we will have. So, what is the density of air is 1.2, right, 1.2 kg per cubic meter. So, once we multiply this 36 into 1.2, it will be 43.2 kg per hour per meter square. Okay. So, this m dot by A is in kg. Okay. So, normally this is volume flow. So, we can write volume flow also, but we can convert it to mass flow rate per area. Okay. Okay. So, this part is known to us now. So, what we need is IT. Okay. And this delta T is given as 0.03 into IT plus 3. So, if we know this IT, then straight away you can calculate what is delta T. So, if we know delta T, then we can calculate what is eta I. So, now our next step is to calculate IT. So, how to calculate IT now? So, already we know the expression for IT, this is IB plus IB multiplied by RB, then we have ID multiplied by RD, then we have IB plus ID, then we have RR, right. Again we have to calculate what is RB, what is RD and what is RR. Okay. Let me give a name of this equation, maybe 2, right. Let us calculate what is RB, RD and RR. Okay. So, this RB if we substitute those values, R B is something like cos theta by cos theta z. Already we have done many exercise. So, before we start, we need to, maybe I can write this other expression as well. So, this R D is equal to 1 minus cos of beta divided by 2, then we will have R R is rho multiplied by 1 plus cos of beta. I think this is plus and this is minus, this is 2. Okay. So, before we start, let us know the values. Okay. So, beta will be here 90 degree, right, because it is a vertical surface. And what will be the phi? So, omega is given as 15 degree and phi will be, we have in the problem, phi is, so I can write here itself, phi is 28 plus 35 by 60. Okay. So, which will be 28.58 degree. Okay. And December 10 is the date. So, we need to know what is n. So, n value we need to calculate. Phi is known. What is the value of phi? 28.58, 28.58 degree, and n will be, so we can start from January, it is 31, then we have 28, then we have 31, then we have 30, 31, January, February, March, April, May, June, July, August, September, then we have October, November, then 10. Okay. So, then this will be calculated to be 344. Okay. So, n is known. So, if we know n, then we can calculate what is delta. Okay. What is delta? We know 23.45 sine of 360 by 365, 284 plus n. Okay. So, this n is nothing but 344. Okay. So, if we substitute there, then what we will get? Delta is equal to minus 23.04 degree. Okay. So, we know all those values now. So, we can calculate RB value now. Okay. So, this RB can be calculated by cos of, first let us start with sine cos theta by cos theta z. Okay. So, sine delta, okay. Then we have sine beta minus phi, okay. Then we have cos delta, sorry, this will be phi minus beta, this phi minus beta, this will be cos of omega, then we have cos of phi minus beta. Okay. Then we have sine phi, we have then sine of delta, then we have cos of phi, cos of delta, cos of omega. Okay. So, if we substitute those values here, then what we will get? So, this RB value will be 1.295, okay, because all values are known to us. Delta is known, minus 23.4, then phi is known, phi is 28.58, beta is 90. Okay. So, that way we can substitute here and we can do the calculation, and this RB is found to be 1.295, and RD, just we substitute the value of beta here, beta is 90, cos 90 is 0, So 1 by it will be 0.5, right. So it will be 0.5. So here it will be 0.5 into 0.2. So this will be rho is 0.2 into 0.5, it will be 0.1. Okay. So now we know RD value, RR value, then RB value. So what we can use? We can calculate IT. Okay. This equation 2, what we have given the name. So this equation 1 equation 2 implies IT is IB RB plus ID RD plus IB plus ID, then we have RR. Okay. So IB value already we know. What is the value of IB? We have calculated, which is 399 multiplied by 1.295 plus ID is 144.0.5 plus IB plus ID is 543 multiplied by RR is 0.1. Okay. So if we do the calculation, this IT is found to be 643.0, okay, watt per meter square. Okay. This IT is known. So once we know IT, then we can calculate what is delta T by using the equation. Equation was not given. So this equation may be star, I can write this is star. Okay. So equation star, delta T is equal to 0.03 IT plus 3. Okay. So if we substitute this value here, then delta T will be 22.29 degree C. Okay. So delta T is 22.29 degree C. So once we know this delta T, then we can go back to the equation 1. Equation 1 implies we will have eta I is equal to mass flow rate mCp dt. Okay. So m, what we have calculated here is 43.2. So this is 43.2. So we need to convert to in second. So it will be 3600, right. So it will become kg per second per meter square. So this m by a is known now. Then IT, what we have calculated is 643, and we will have Cp is 4.18 into 10 cube, and then we will have delta T. So this delta T is here 22.29. Okay. So now if we do the calculation, so this eta is found to be 41.88%. Okay. So this efficiency is found to be 41.88%. Okay. So what we have shown here, so in case of transpired unglazed collector or say unglazed transpired collector, if these radiation parameters are given, then we can calculate what will be the efficiency of the collector, right. Okay. So what we have learned in this presentation, so we have basically learned about the fundamentals of solar air heaters, what are the advantages of using this solar air heater and what are the disadvantages of using these solar air heaters, and also we have analyzed the performance systematically, and also we have seen the functioning of different solar air heaters and the research trends, and finally we have solved one numerical exercise to strengthen the understanding how to calculate efficiency of a collector. Okay. So thank you very much for watching this video. Thank you.